All right, guys, welcome back. This is going to be our 7.3 part 1 instructional video. Again, as you're going to notice, the part 1, part 2 is happening more frequently as we get into the further along into the content. Just because it gets more complex, problems take a little bit longer, and I don't want you to have to sit there and watch a 45-minute video. So we're going to go through the first part of 7.3 today, and what 7.3 is going to be all about is elimination. Okay. Again, I feel like I keep saying this in the videos. If you have not watched 7.1, both parts, and 7.2, both parts yet, please go back and rewatch those. Those are going to give you insight into what systems of equations are, what a solution looks like, and 2 different methods for solving them. So please go check those out before you watch this one. So what we're going to learn about in 7.3 is a way of solving a system of equations known as elimination. This is an alternate to substitution and to solving a system by graphing. And we're going to talk about why we do that in a second. But first things first, I want to kind of re-go over a topic that you all should be incredibly familiar with. I have a problem on the board that would have been common in the very early parts of chapter 2. Really, it's only a 2-step equation. And I know you all will tell me, if I said, how do you solve the following? You all are going to tell me the first step is to add 10. Again, go back and watch some of the early chapter 2 videos if you aren't sure as to why we're adding 10 first. But you all are going to tell me to add 10, and you're going to tell me to add 10 to both sides. And there are 2 key ideas in that I want to kind of retouch on. Number 1, you're telling me to add 10 to undo the minus 10. Okay? And what we do is, broadly speaking, we use inverse operations to isolate variables. Use inverse operations to isolate variables. Okay? What I'm doing here is, when I see a minus 10, I'm going to add 10 so that to the left side, because when I have minus 10 plus 10, that equates to 0, leaving me with just 3x on the left side. I am doing an inverse operation. I am doing the opposite of subtracting 10 by adding 10 in order to help isolate the variable, because this effectively cancels out the minus 10 when I introduce the plus 10. But I also do it to both sides. And broadly speaking, what I do to one side, I must do to the other. What I do to one side, I must do to the other. This goes back to the idea of equality. These are equations. I have 2 things that are equal. 3x minus 10 equals 2. We're saying they are equivalent. The best analogy, if you look at the camera section, is it's a balanced scale. And if I add 10 to one side, my scale has become unbalanced. And in order for this to stay an equation, for these 2 things to be equal, I must also add 10 to the other side. Okay? So inverse operations and doing the same thing to both sides. Those are 2 critical ideas that we've learned about before that are going to be key to elimination. That'll be key to elimination. Now, before we dive into an example and some definitions, I want to discuss why we need elimination. And to do that, I'm just going to come up with a quick problem here. Actually, I'm going to come up with 2 systems of equations. These are supposed to be y's, not x's. So what you can see here is I have a system of equations in blue and I have a system of equations in red. Now I want you to pause the video and I want you to think to yourself, which system of equations would I rather solve using substitution? Which system of equations would I rather solve using substitution? So hopefully you've thought about it, and I hope that your answer turned out to be this one over here. And let's dig into the reason why. Why is the one on the left the easier one to solve? Well, when we start to substitute, and again, if you're not familiar with substitution, please watch the 7.2 video. Substitution requires us to get a variable by itself so that we have something that we could plug into the other equation. So when we think about what variable is going to be by itself, we don't have any variable by itself in either system, but the easiest one to get alone in the blue system would be y in the bottom equation. Why? Because it doesn't have a coefficient. Okay, if it had or by not having a coefficient, we're going to have to do no division and get any sort of nasty fractions or anything. Whereas if we look at the red system, man, there is no good variable to get by itself. All of our 4 variables, our 2 x's and our 2 y's, have coefficients. I'm going to end up with some sort of nasty fraction if I try and do substitution with that problem. This is why we develop, or why we learned, or we're going to learn elimination. You see, 7-1 was great with graphing. We had a great visual. We would find the intersection point, and that intersection was the solution, the xy coordinate pair that made both equations in the system true. But we ran into a problem. What happens if our solution's a decimal? Graphing by hand isn't going to be super accurate. So we solved using substitution, and that was great. But again, substitution comes short when we hit problems like we see here in red, or systems that we see in red. Because it's going to be very difficult to isolate a variable, and the substitution is going to be nasty with decimals and fractions. Elimination helps us to solve systems of equations that are in standard form where there isn't an obvious variable to get by itself. Now, before we dive into the definitions of elimination, I think the easiest way we can kick this off is by solving an example. So I'm going to set up a system of equations. 5x minus 6y equals minus 32. And 3x plus 6y equals 48. 3x plus 6y equals 48. Okay, I have a system of equations here. And if I would go to solve this with substitution, it's going to be nasty. There isn't a clear-cut variable I can get by itself without having to deal with a coefficient in some sort of division. If you don't believe me, try and isolate one of those variables. You're going to get some nasty fractions and decimals. So I need an easier way to solve this. So what could we do? Well, let's pretend for a second. Maybe I rewrite the equations as stacked, right? I'm going to temporarily rewrite the equations as stacked equations. Okay, just moving the 1 over here. Now, without even thinking, I want you to take 5 seconds and I want you to think about what variable, when you see the stacked set of equations, should we get rid of? 5, 4, 3, 2, 1. Well, even though you have no idea maybe how it'll work, I hope your gut said why. Because you probably looked at the x's and said, man, I don't see anything there. But you noticed something unique about the y's. What you noticed is that, hey, I see a minus 6 and a plus 6. That's kind of weird. Hey, minus 6 plus 6, hey, that gives me 0. And that's probably, whether you realize it or not, what your brain observed. And you're absolutely right. Our whole goal, if you think back to substitution, was to take our two variable equations and develop one variable equation. Why develop a one variable equation? So I could solve for the variable, get x or y equals some number, and then we are well on our way to finding the solution. The logic here is the same. I want to get a one variable equation because I know how to solve those, but substitution isn't going to allow me to do that. But I notice when I stack these equations up, hey, if I would add 6y and minus 6y, hey, you know what? That would cancel. So let's go back to the original way it was written. When we stacked them, what we observed is if I take this 3x plus 6y and I add it to the left side, if I add it to the left side, I'm going to end up with something nice. 5x minus 6y plus 3x plus 6y, right? Maybe we could write that out over here so you could see it a little bit better. or you could just view it as stacked, either way. What we're going to do is we're going to combine our like terms, right? 5x and 3x gives us 8x. Minus 6y and 6y add to be 0y. So this whole green equation all just sums to be 8x. And lo and behold, by taking my second equation and adding it to the left side of my first equation, we ended up with something really simple, 8x. But here's the catch. What you do to one side, you must do to the other. Which means I also need to add 3x plus 6y to the right side. Now I would pause you on writing stuff down. Don't write this quite yet because I want to show you something. If I go through with that, I'm going to end up with negative 32 plus 3x plus 6y. And honestly, when I look at my black equation and now what I have in blue, I don't feel any closer to solving the problem. I have two variables, and in fact, I feel like, honestly, I'm a little bit further away. So what went wrong? We felt like we were on such a good path. Well, what we're getting tripped up by is what we do to one side of the equation, we also must do to the other. What we do to one side, we also must do to the other. And we have to do this to keep the equation balanced. But what's another way I could think about this? Well, we're almost going to reintroduce part of a concept of substitution into our equation solving. You see, where I ran into trouble is by adding the 3x plus 6y. Because negative 32 plus 3x plus 6y doesn't simplify down because none of them are like terms. So how could I do this a bit differently? Well, I'm going to use my second equation and this idea of substitution. All of chapter 7, or largely in 7.2, we've been talking about how if something equals something else, I can substitute them for one another. When I see 3x plus 6y equals 48, that means anywhere I see a 3x plus 6y, I can plug 48 in. So instead of adding 3x plus 6y to 32, I'm going to add 48. Why can I do this? Because 3x plus 6y equals 48. I'm still keeping the scale balanced. Just like if you go through the drive-thru and you hand them some dollar bills and they give you food, well, they didn't give you your money back. They didn't give you back the same thing. It was an equal transfer. They gave you the appropriate amount of food for the amount of money you gave them. The same idea is happening here. I'm metaphorically taking the 3x plus 6y and receiving the 48. The 48 and the 3x plus 6y are the same. They are worth the same in this problem. So while I didn't add 3x plus 6y to the right side, I'm still doing to one side what I did to the other because 48 equals 3x plus 6y. Now that's immensely nicer because now I have some like terms I can combine. Negative 32 plus 48 is 16. And holy cow, I've got a much easier problem to solve. And I quickly find out that x equals 2. This is the idea of elimination. I'm going to try and get rid of one of my variables, but what I do to one side, I must do to the other. But using the idea of substitution, I can still get a nice equation to solve. So we find out that x equals 2. X equals 2. So we get x equals 2. And that's only half of our answer, though, because we know at this point a solution to a system has to have an x and a y coordinate. So I'm going to plug, just like I did with substitution, my x equals 2 back into one of my original equations. And I'm going to solve for y. And again, hope this should not be new to you all. And we end up with y equals 7. Now again, we've done a ton of work. We need to understand what our solution is. What we're saying is these two equations in black will intersect at the point 2, 7. 2, 7 is the only combination, the only xy pair that will not only make one equation true, but will make both of them true. And we found it using elimination. Could you have found it using substitution? Yes. But it would probably be a little bit nastier. Now, if you're sitting there thinking, man, elimination's a lot of work. This is messy. I can't do this. I promise as we go on, it'll get a little bit better. But before we do, let's talk about our key ideas. And the key principles that I want you to write down are what you add to one side, you must add to the other. So take a second and write these down. But please understand, what you add to one side, you must add to the other. While we are holding this principle true, it doesn't look like how we've used it in the past. Because we're not adding the same exact thing visually to the both sides. Are they worth the same thing? Yes. In that last problem, when I add 3x plus 6y to the left side and 48 to the right side, they are worth the same because of our second equation, but they look differently. So what you do to one side, you must do to the other, but it's going to look a little bit different than how we've seen it in the past. And then, of course, our goal is to get rid of one of the variables. This will give us a one variable equation that we can then solve. So let's work through another example together. Let's do 6x minus 3y equals 3, and negative 6x plus 5y equals 3. And you'll notice I already went ahead and stacked my equations. I would recommend automatically stacking your equations if you're ever thinking about doing elimination. Stacking them is just going to make them a little bit easier. And I think visually it's easier to see what your variable will make sense to eliminate. Kind of like how I showed you in the last problem. So again, bear with me. If elimination is confusing, I think it'll get better. So looking at this problem, we have 6x minus 3y equals 3. And negative 6x plus 5y equals 3. Off the cuff, substitution is going to be nasty because there's no variable. It's easy to get by itself. But what I notice is the interesting relationship going on with the x's. 6 and minus 6, when I add those together, will cancel. Now, don't do minus, right? We don't want to do 6 minus negative 6. That will be 6 plus 6 and give us 12 because of the double negative. But if I do just add the two together, my x variable will be eliminated, okay? So what I do is I add the left sides of the equation together. 6x minus 6x gives me 0. Negative 3y plus 5y, I also want to add together because I still want to have a variable. Okay, I still want to have the y variable because now I can figure out what it is since the x's canceled out. But what I do to one side, I must do to the other. Now, does that mean I'm going to add negative 6x plus 5y to the other side? No. Do I need to? Yes, I do need to add negative 6x plus 5y to the other side because what I do to one side, I must do to the other, but there's an easier way. Since negative 6x plus 5y equals 3, instead, I will just add the right sides together. This is where the stacking can be super nice. We add the left sides of the equations together. We add the right sides of the equation together. If you want to see it more visually, if I start with 6x minus 3y, what I'm saying here equals 3. We said we wanted to add 6x, or we wanted to add negative 6x plus 5y to the left side. But what we do to one side, we must do to the other. But I don't want to add negative 6x plus 5y because that won't simplify the problem. Instead, I want to add what it's equal to, which is 3, since 3 equals negative 6x plus 5y. By doing this, I've met the criteria of what I do to one side, I do to the other. And by doing it this way, I'm going to get a much nicer equation. So what you see me doing in blue and red here is really what I'm doing when I put these plus sides in and I'm adding the stacked equations. So when we do 3 plus 3, we get 6. Divide by 2, and we get y equals 3. Y equals 3. Using this idea of elimination, and what I do to one side I have to do to the other, with a hair of substitution, I can get a really simple one variable equation. Now where do we go from here? Well, if our y coordinate is 3, that's great, but we got to find the x coordinate. So I plug it back into one of my originals. Maybe I plug it into the bottom one. Okay, it doesn't really matter. So I plug it into the bottom one, and I get negative 6x plus 5 times 3 equals 3. Negative 6x plus 15 equals 3. Subtract 15 from both sides. Negative 6x equals negative 12. And I get x equals 2. Again, how could I check my work? Well, plug it into a calculator. 6 times 2 is 12. Negative 3 times 3 is negative 9. 12 minus 9 does equal 3. Negative 6 times 2 is negative 12. 5 times 3 is 15. Negative 12 plus 15 does equal 3. This is, in fact, the solution to our system. And we didn't have to go through any messy dividing of coefficients. Okay? So again, elimination, get rid of one of the variables, and make sure what you do to one side you do to the other, but we do that with some substitution involved. Let's look at one more example together. Suppose VB Basketball sells 292 tickets for their upcoming game. An adult ticket costs $3 and a student ticket costs $1. The VB Athletic Boosters collect $470 in ticket sales. Write and solve a system of equations to find how many tickets of each type were sold. We need to write and solve a system of equation to find out how many tickets of each type were sold. Okay? Well, automatically off the bat, if we're solving this, I'm not sure how many tickets of each type are sold. It's what I'm asked to find. So I would go ahead and I would set a variable, number of student tickets. Maybe I say A is number of adult tickets. Okay, I'm trying to find the number of student tickets and number of adult tickets. But unlike the previous problems, I don't have a system of equations, so I have to create that. So let's use the information given. We always like to look for totals here first in our word problems. So I noticed this 470. But what I'm going to do is I'm going to be specific. Because unlike previous chapters where we've only looked for one equation, we're working with multiple equations now. So let's establish what our equations are about. My first equation, when I look at this 470, is going to be all about money. Right? The Van Buren Athletic Boosters make a total of $470. Now, what is making up that $470? Well, an adult ticket is $3, and a student ticket is $1. Why are we adding? Well, because the combination of the sales from the adult tickets and student tickets are going to make up your total ticket proceeds. So we got $3 for an adult and a student costs $1. So how can I write that? Well, if I sell 2 adult tickets, I make $6. If I sell 3, I make $9. If I sell 4, I make $12. What am I doing? I'm taking 3 and I'm multiplying it by the number of adult tickets, which we said was going to be A. Same thing for S. That'll be the number of student tickets. Now again, why do we need to set up a system of equations? Because there's multiple things going on here. And even then, with our green equation, well, that's wonderful. We can't just figure out how to meet this $470, but we also have to meet the criteria that 292 tickets were sold. 292 talks about the amount of tickets. Again, it acts as another total. What's making up the amount of tickets? Well, we sold some number of adult tickets and some number of student tickets. We don't know how many, but that's how many we sold. or that's how many we don't know how many specifically, but those are the variables we're using to represent number of tickets. So we have the system of equations set up right here. And while we could use substitution in this case, we could use substitution because it would be fairly simple. I'm just going to erase this one coefficient just because it doesn't really do anything for us. Anything times 1 is itself. While it would be very easy to solve for a and s in the bottom equation or even s in the top equation, we're going to practice elimination, but you could solve this one with substitution. So how would elimination work? Well, let's look. We always try and get rid of a variable, just kind of eyeballing it, seeing how we could cancel one. If I add the 3a and the a, I'm going to get 4a. That doesn't do me any good. If I add the s and the s, that'll give me 2s. Again, not any good. So addition clearly isn't going to help me. But if I subtract the s and the s, if I subtract the s and the s here, that might get me somewhere because one s minus another s, I have no s's. Now we got to stay consistent with the operation we use throughout elimination. So I'm going to subtract the s and the s, then I'll do 3a minus a. That'll give me 2a. And on the right side, we're looking pretty good because we have a single variable. But what we do to one side, we must also do to the other. But we're not going to subtract a plus s from the 470. Instead, we'll use what a plus s equals, which is the 292. And we'll subtract 292 from 470. And so when we do that, we end up with 470 minus 292. I believe it's 178, but let me check my work. We end up with 178. And again, we are now on our way. We have a very easy one variable equation to solve. 178 divided by 2 will be 89. And that is the number of adult tickets we sell. Number of adult tickets. Well, we need to figure out the number of student tickets. So we plug our variable back in. I think the bottom one's probably a little easier to work with. 292 equals 89, since we know that's what A is, plus S, which leads us to finding that 203 is the number of student tickets. Okay? 89 adult tickets and 203 student tickets. Folks, I hope this makes sense. I hope while elimination, when we initially learn it, is very difficult, I hope you're starting to sense a process and hopefully it helps you solve systems of equations a little better. Again, this is only part 1. Part 2 will be coming, so stay tuned for that.